Hi guys, welcome back to my channel. Today I want to talk about electrochemistry. And before we dive into the galvanic cell and electrolytic cell, I want you to pay attention to the table on the left where you see that the different metals can have different reduction potential, right? For example, we see this copper here, it has a 0.34 volts potential, reduction potential, whereas the zinc has a lower reduction potential at negative 0.76, right? And then by saying that copper has a higher reduction potential than zinc, we mean that copper is more likely to be reduced than zinc, right? And then we also know that reduction means gaining the electrons. So we can also say, oh, copper with a higher reduction potential are more likely to gain electron than zinc does, right? Okay, and then another thing you may have noticed from the table is that when the metals are in their charged form, they're usually cations, right? They're in their aqueous form. They're dissolved in aqueous, right? Whereas the solid form of the metal is after the charged cation aqueous form of the metal gained electron, right? After they gained electron here, and then they will form this neutral solid form of the metal, okay? All right, so now we're ready to dive into the galvanic cell, okay? And then as you can see, the galvanic cell really has like two parts, right? And then each part is called a half cell, okay? And then two half cells make this one whole cell, okay? And then one half cell is going to have the oxidation reaction happening, and then the other half cell is going to have the reduction reaction happening. So this whole cell is having some redox reaction, we say, right? And then by convention that we say that the oxidation reaction is always happening at the anode side, okay? And then the electron movement is always from the anode to the cathode, okay? You will see what I mean in just a second, okay? And then the convention is the cathode side is where the reduction reactions happen, okay? All right, so we can really just write out what specific reduction and oxidations are happening on these two half cells, okay? All right, so let's look at the cathode side first, okay? So the cathode side, we said that is the reduction reaction that's happening. So meaning that it's the copper 2 plus that is gaining electron and forming the solid copper, right? Whereas the anode side where oxidation that's happening is just a flip of the reduction reaction, that the zinc solid is getting broken down into the zinc cation aqueous form plus the electron, right? So that is the two different reactions that's happening in the two half cells, right? One being the oxidation reaction again in the anode side, and then the reduction reaction in the cathode side. And then some people use the red cat to memorize that cathode is where reduction happens, okay? All right. Okay, and then we can also write out the net potential of this cell by adding the oxidation potential of the anode side plus the reduction potential of the cathode side, right? And then we know that the reduction potential of this copper is a 0.34, right? But what is the oxidation potential of zinc, right? This table tells us the reduction potential of zinc, not the oxidation potential of zinc. But if we just flip it to positive 0.76, then we know the oxidation potential of zinc is 0.676, right? Plus the reduction potential of copper, which is 0.34, I get 1.1 volts. That gives me the net potential of this galvanic cell, okay? All right, and then when you have this positive potential of the cell, we know that this is a spontaneous reaction, right? Both the reaction and the oxidation reaction, they're both spontaneous, okay? And then you see that I said the electron flows from the negative side to the positive side, right? So the negative side is really the anode side, and then the positive side is really the cathode side, okay? And then the flowing of electron is basically, you see that the zinc, the oxidation reaction here, the solid zinc is basically broken down into electron and the aqueous zinc 2 plus, right? So that we have this basically electron supply that can flow from the anode because oxidation happened at the anode side. And then the reduction side is where the electrons are received, right? The electrons are received so that the copper 2 plus can react, can have this reduced reaction, can be reduced, right? Gaining electron, receive those electron and form this copper solid, okay? All right. And then as you can see, more and more this copper solid, as more and more this copper solid is formed, I can really just draw a bulge here, right? Noting that there's a more and more this neutral copper solid that's formed, right? And then the other side, since I'm losing more and more mass of this electrode, right? This piece of solid metal, we call it electrode. So I can really just show the shrinking of this zinc electrode, right? Whereas the copper electrode is really gaining the mass, okay? All right, and then because the anode side, the zinc 2 plus is formed more and more, right? So we basically build up this positive charge on the anode side. And then the cathode side, we're getting less and less copper 2 plus because a lot of the copper 2 plus are receiving electrons, are gaining electrons to form this copper solid, right? So that we have we can see relatively we have more negative charge that's building up on the cathode side, and then we don't want the buildup of the charge, right? Because we want the electrons to keep flowing, right? And then that is the function of this salt bridge, right? Salt bridge has either Na plus or Cl minus, and sometimes it can be KOH or something else, okay? So this Cl minus will flow to the anode side to balance out the zinc 2 plus, okay, to balance out the buildup of the positive charge at the anode side. And then the Na plus will flow into the cathode side to build up the relatively negative charge building up at the cathode side, okay? So that's the purpose of the salt bridge, okay? And then also that we say that the net potential of the cell is a positive 1.1, right? So if you will have a voltmeter here, you will see that the number shows 1.1 volts, okay? And then interestingly that the voltmeter itself, it's in the middle of the cell. I can't say circuit, but it kind of acts like a circuit, right? Because the flow of the electron is basically current, right? But current really flows different direction than electron flow, okay? That's another topic. But anyways, my point is saying that this voltmeter in the middle of the cell itself, even though it measures like the potential difference of the cell, but it's also acting like kind of like a resistor. And then the unit for the resistor is ohm, okay? And then if you don't have this voltmeter in between, you have a light bulb, let's say, okay? And then because of this spontaneous flow of electron, then we will light up the light bulb, right? And then the light bulb, even though it's being lit up, because there's an electron flowing, right? But the light bulb itself can also be a resistor. It can cause some resistance of the electron flow, okay? So on MCAT, this electrochemistry galvanic cell is they always test this with the equation I equals I just blank. Okay, V over R, okay? So let's say this is 1.1 volts, right? And then let's say the voltmeter carries, or the light bulb carries 2 ohms of resistance, okay? Then you can account how many amps of current that's flowing through this apparatus, okay? All right. I think that's everything you need to know about the galvanic cell. And then this is really spontaneous because really the the metal with a higher reduction potential is getting reduced, okay? And then the metal zinc with lower reduction potential is getting oxidized, okay? And then we can also say that zinc is the one with higher oxidation potential, and then zinc is the one that's getting oxidized. So whatever how you say it is just spontaneous, okay, thermodynamically. Okay, so now let's look at a electrolytic cell, okay? So the electrolytic cell is really just opposite of the galvanic cell, okay? How so? Let's look at this. So the electrolytic cell, we also have a anode side having reduction reactions, and a cathode side will have the anode side will have the oxidation reaction, and a cathode side will have the reduction reaction, right? But the difference is that the reduction reaction now, it's really the zinc that's getting the electrons and being reduced, right? This is counterintuitive because zinc really has a lower reduction potential, as you see from the table on the left, right? So zinc has a lower reduction potential, but it is being reduced in the electrolytic cell. And then copper, on the other hand, is being oxidized, even though copper has a higher reduction potential, right? So if now you add up this zinc's reduction potential plus the copper's oxidation potential, you will get a negative 1.1, okay? So this negative net potential of the cell really means that it's non-spontaneous, right? It's against the favorable energy, the favorable thermal energy, right? And then, but how do we drive it, right? If it's non-spontaneous, do we heat it up, or what do we do to make it happen? To make zinc being reduced, to make copper to be oxidized, right? So the idea is that the electrolytic cell is where we provide some electrical energies to the cell, so that the electron flow really still goes from anode to cathode, right? As you see that I draw here, it's still going from anode to cathode. But the idea is that the cathode side is the side that receives the electron and getting reduced, right? As you can see that the electron, right? The electron goes from the negative voltage here and then to this zinc, to this beaker with zinc, and then these aqueous zinc cations metals, they will receive this electron and form this neutral solid zinc. As you can see, I drew this bulge of this electrode, meaning that it's gaining the mass, right? And then the electron from the copper side, from the anode side, will flow out, okay? Meaning that more and more this aqueous, this cation copper is formed, right? And then we're losing more and more of the solid copper. So that's why you see this shrink of the mass of this solid copper electrode, okay? So this is about electrolytic cell, okay? And then we also see that we have some negative charge buildup in the cathode side of electrolytic cell. So the salt bridge, in this case, to neutralize the charge, we have this positive sodium that's flowing into cathode side. And then the building of the positive charge in the anode side of the electrolytic cell requires the negative chlorine to flow into, and then the overall charge can be balanced, okay? So that's all about galvanic cell and the electrolytic cell. There's a lot. I hope that's helpful.